In the previous episodes, we focused on the internal functioning of a large language model. We learned about transformers architecture and concepts such as tokenization and embeddings. In this episode, we'll proceed to learn how applications can interact with a large language model. As application developers, we communicate with model through APIs that are exposed by them. At a high level, the interaction is very simple. Our application sends a prompt, which is converted into input tokens and sent to model. The model processes these tokens and generates output tokens, which are returned as response. Although this looks like a simple request and response, a tremendous amount of computation happens inside each API call. The model tokenizes the input, performs attention across all tokens, generates a probability distribution for the next token, and selects the next token based on sampling strategy. It repeats the process until the entire response is complete. Fortunately, as application developers, we do not need to implement any of this. For us, the API call abstracts away all the complexity. When we invoke a large language model, we primarily pay for three things. First, the number of input tokens that we send. Second, the number of output tokens that model generates, which are more expensive than input tokens because generating them requires repeated inference. And finally, the number of API calls. While a single chatbot response may require only one call, more advanced applications such as agentic workflows often invoke model multiple times, increasing the overall cost for a single run. We can control models' behavior using some inference parameters. These include temperature, which controls how deterministic or creative the generated response should be. Lower values make model more focused and predictable, while higher values encourage it to explore more alternatives. The second inference parameters are top P and top K, which define the sampling strategy of the model. They limit the set of candidate tokens that model can draw the next token from. The third parameter is max tokens, which is basically the maximum number of tokens that model is allowed to generate. It acts as upper limit on the response length. Most model providers provide these inference parameters to be set on LLM call. Let us look at some of these inference parameters in a little more detail. As I shared, temperature controls how predictable or creative the response will be. It is important to understand that temperature does not change what model already knows. It does not make model smarter or give it any new knowledge. Instead, it changes the probability distribution before next token is selected. If you look at the left side where temperature value is 0 2, you will notice that probability distribution is very concentrated. One token has much higher probability than the others. And because of this, the model will always select the highest probability token. The response tends to be consistent, deterministic, and predictable. If you ask the same question multiple times, you're likely to get very similar answers. And this is ideal for tasks such as question answering, summarization, code generation, data extraction, where consistency is important. On the right side, you see an example of a high temperature, which is 1. The probability distribution is much flatter instead of one token dominating. Several tokens have similar probabilities. As a result, the lower ranked tokens now have much higher chance of being selected. And this is good for use cases where we need more diverse and creative responses, such as creative writing, brainstorming ideas, story generation, any marketing material generation, generating multiple alternatives for a problem, etc. Although there are no fixed rules for how you should use this, as you can experiment for your use case, typical values can range from zero point 0.2 to zero point 0.9, with zero point 0.7 being a common default that provides a good balance between consistency and creativity. Now, let us look at the two inference parameters that decide the sampling strategy. The first is top P sampling. This is also called nucleus sampling. Here, instead of selecting a fixed number of tokens, top P keeps adding the most probable tokens until their combined cumulative probability reaches a specified threshold. In this example, P is set to zero point 0.9, which means that we keep adding tokens till the cumulative probability of all the tokens reaches 90%. After which we stop and we select the next token amongst the selected tokens. Top K is another way we can control sampling strategy. In this case, instead of providing a percentage, we provide a fixed number. Here K is equal to 5, which means we select top 5 highest probability tokens and pick the next token from amongst them. Everything below rank 5 is discarded. In practice, top P is used more often than top K because it adapts to model's confidence. If model assigns 90% probability to top 3 tokens, then top P will limit the sampling from these 3 tokens, whereas with top K, we will include 2 tokens that have very low probability in the candidate set. So the key takeaway here is that temperature changes the shape of probability distribution. Top P keeps enough tokens to reach a target cumulative probability, and top K keeps a fixed number of highest ranked tokens. After either method selects the candidate set, the model randomly samples the next token. If you think about it, even top P and top K influence the creativity or deterministic nature of the model. Now that we understand what happens during the LLM invocation and the key parameters that influence the behavior, let us see this in action. Before we begin our demo, I wanted to show you that I have already set up my local machine by downloading Ollama, which lets you run open weight models locally on your machine. I will download and run Meta's Llama 3 8 billion parameter model locally on my machine. Before we begin, let us run the Llama 3 8 billion parameter model. Throughout this course, we will be using Jupyter notebooks for our demonstrations as they let us combine explanations, code, outputs in a single interactive document, which makes it easy to experiment with ideas and see the results immediately. It is one of the most popular environments for learning, prototyping, and exploring AI and data science. For this hands-on demonstration, I will use Jupyter Lab, which we will launch through Anaconda distribution on my local machine. It is very easy to download and set up Anaconda on your local machine. It provides a simple way to install Python, Jupyter Lab, and many libraries that are commonly used in AI, machine learning, and data science. It eliminates much of the setup complexity, making it easier to start learning rather than worrying about configuring the environment. I would encourage you to download and install both of these in your local machine if you want to experiment locally. This is the Jupyter notebook, and as you can see, it has comments and different cells that we can execute using these buttons over here. Let us first install Ollama, which will help us interact with Ollama that is running locally on our machine. This cell has the model invocation. We have a variable prompt with the user's input. Invent a completely original joke about quantum computers. And then we have this API call, ollama.chat, where we are first setting the model because Ollama can download and run different models at the same time. So we need to provide the model that we are trying to invoke here. And then we have a list of messages where each message has two important pieces of information. The first is the role, which tells the model who is speaking. You can think of it as labels in a movie script. And then we have the actual prompt that is being sent to the model. For any conversational application, you can also augment the model's response to this list of messages. In that case, the role will become assistant and the content will be model's response. This way, you will have the entire context of back and forth conversation between user and the model. Many model providers also support messages with the role system, where the developer can add instructions for the model. In this case, we only have one message from the user, which is the prompt that we want the model to answer. And then we have a joke from the model. Why did quantum computers go to therapy? Because it was struggling with superposition and also its qubits were falling a little entangled with their emotions. Now let us explore the inference parameters that we talked about. Different model providers provide different ranges of values for temperature. Some providers, such as OpenAI and Google, support 0 to 2 as the range, whereas Anthropic supports 0 to 1 as the range. Ollama supports anywhere from 0 to 5. So let us try this call with temperature of 5. Top P is 90%, top K is 40, and the maximum length of output tokens is 1000. And then we have the same joke. Why did quantum computers go to therapy? Because it was struggling with superposition in its love life. It wanted to be in multiple relationships at once. Let us try again. I'm hoping we will get a new one. So, this is a different joke than the previous one. Let's run it one more time. And as you can see, it's picking a different joke every time because the temperature is pretty high, actually at the maximum. So, the response is being creative. All right, let's change this behavior by setting the temperature to 0. And here we have this joke which says, why did quantum computers go to therapy? Because it was struggling with superposition of its emotions. It was both excited and terrified at the same time. And you can see even in the second invocation, it returned the same joke. Let's try one more time. Again, the same joke. So as you can see, with temperature to 0, it is always picking the most probable answer. Whereas with the high value of temperature, we were getting a different joke every time. Now let us see if we can tweak this behavior by tweaking top P. And we have the same response. And we are getting the same response. If I make it zero point 0.7, let's see if we get a different response. And see, we got a different response. So even top P affects the creativity because it limits the candidate token set. So a lower value of top P will limit the candidate token sets to only top values, whereas with the higher value, we will have more candidates in the selection pool and a higher probability of getting a different response. Many of the labs in the series will also use Amazon Bedrock as the model provider and Nova Pro as the model. And I want to show you how Bedrock API can be invoked. You will notice that the API call syntax could be different and there could be difference in the message structure, but the components of the LLM call remain the same. So here in this cell, I am installing Boto 3, which is the Python SDK for invoking AWS services through code. And then I'm setting a programmatic access to the AWS account by setting access key and secret access key. We will create a client for interacting with Bedrock service. And this cell shows how you can invoke Amazon Nova Pro using Amazon Bedrock's Invoke Model API. Don't worry about memorizing anything because writing code is very easy these days. The only thing that I want to show is that most model providers have similar components in inference call. Nova Pro gave us a different joke. Why did quantum computer bring a ladder to the party? Because it heard the Wi-Fi was in a higher qubit. Amazon Bedrock also provides a higher level API called Converse API. Throughout this course, you will see me invoke Bedrock models either using invoke model or Converse API. The difference between these two is that Converse API is a higher level API. Converse API abstracts away any model specific differences in the request structure. It automatically converts our input prompt into the structure that model requires. Again, we have the role, content, and the inference parameters. We can also specify top P, top K. And as a last step in this demo, I also wanted to briefly touch upon LangChain's Chat Bedrock Converse API. LangChain is a framework that provides modular components for building generative AI applications. It has a module Chat Bedrock Converse that allows us to invoke Bedrock models through LangChain. Later in this series, when we use LangChain for workflow implementation or agent implementation, you will see that there are certain times when I use Chat Bedrock Converse. It does exactly the same thing as previous API calls, but with a different syntax. So this was a quick demo of how you can make an LLM call from your code. Depending upon the model provider of your choice, you may choose a different SDK, but the components of the LLM call remain the same. Let us take a step back and put everything that we have learned so far in perspective. So far, we have focused on understanding how the large language model works, and we have also learned how to invoke the large language model from the code. But if you're an enterprise application engineer or architect, the model is only one piece of the puzzle. The next layer is the application. This is how users interact with the model, whether through a chat interface, an API, or an application that you can embed in your existing business workflow. However, the real engineering challenge lies in the system that surrounds the model. In production systems, the success is determined by how well you build the environment around the model, which includes connecting enterprise data, securing application, implementing guardrails, monitoring quality and cost, managing governance, ensuring reliability, and integrating with existing business systems. In other words, model provides intelligence, but the system delivers the business value. Therefore, in the rest of the series, we will focus on designing complete enterprise AI systems that are secure, scalable, observable, and production ready.